Today we're going to be talking all about the alkene functional group. The big idea here is that alkenes are much more reactive than alkanes, and also that benzene has really unique properties. So alkenes are a lot like alkanes in a lot of ways in terms of physical properties. So in terms of physical properties, like alkanes, these are nonpolar. So they all have C and CH bonds, which are generally nonpolar. So they're not very water soluble. They're insoluble in water. And they have these weak London dispersion forces in general. Um, and, they're a lot less dense than water. So all of these things they really have in common with alkanes. So there's nothing new to learn there. They're less dense than water, float on water. They're nonpolar, so they're really insoluble in water, and they have weak London dispersion forces. Now, alkanes, generally speaking, we burn a lot of them in our everyday lives, so they're really combustible. They're flammable. We burn methane to heat our homes and hot water heaters. We burn propane at our gas grills and those white propane tanks. We burn octane, generally speaking, around 8 carbon chain length for gasoline for fuel. So we're burning and taking advantage of that combustibility of alkanes. So, since we do that a lot, it might seem like they're really reactive, but in a chemistry sense, the alkanes are considered pretty unreactive. And it's really having these double bonds or being an alkene that adds a lot of reactivity. So it's when we see these double bonds in our molecules, and then we find our alkene functional group, that we tend to see a lot more reactivity. So in this first molecule, CH2 double bonded to CH, and then a single bond to CH, and then, two methyl groups after that. It's that first CC double bond or that alkene that's going to have a lot higher reactivity. Then here, instead of cyclobutane, we have a square with a double bond, so cyclobutene. In both of these cases, we have added double bonds or alkenes. So you can have alkenes in straight or branch chains. You can have alkene double bonds in rings. And then when we have that hexagon with what looks like alternating double, single bonds, we've got our special molecule benzene. Now, in reality, those bonds aren't alternating double, single. They're more like a bond and a half each. And so lots of times people draw this circle, a ring in the middle of the hexagon to represent the fact that these electrons in that double bond are being actually shared evenly. And so benzene is an example aromatic compound. Now, aromaticity is complicated, and the rules to aromaticity are not something we're going to study here. But it's important to just note that benzene falls in this important class of compounds that's called aromatic. Okay, so why are alkenes so important to us? Well, they're really important to health, and they're really important in the human body. For example, this just 2 carbons that have a double bond. So we've got 2 carbons with a double bond. And normally when we have 2 carbons, we fill those 2 carbons in when they're bonded with 3 hydrogens on each. And we'd say that that is totally saturated. And that would have been our alkane ethane. Eth for 2 carbons, ANE for all single bonds, but ethane is totally saturated. So it's all filled up with all the hydrogen atoms that it can have. However, ethene here, which is 2 carbons with a double bond, is what we call unsaturated. It's not filled up with all of the hydrogen atoms that it could have. It's not filled to capacity with hydrogen atoms. So ethane follows our CnH2. Oops, that should be an H. Sorry, I'm just going to go with this. Follows that CnH2n plus 2 rule. Whereas when we have a double bond, that's actually going to be CnH2n will cover the hydrogens because you only have exactly as many hydrogens as carbons whenever you have a double bond. So our rule when we have double bonds is going to be CnH2n. whenever we have a double bond present, a double bond, or a ring, or a cyclo. That'll be our rule for figuring out the carbon to hydrogen ratio in the formula. So this isn't always called ethene. Sometimes it's commonly known as ethylene. And ethylene is the ripening chemical that bananas give off, and that ripens fruit. And so sometimes you'll hear to put a banana in a paper bag with fruit to ripen it, and that's because that ethylene will ripen other fruits as well. And why do we have tomatoes in the middle here? Tomatoes are known to contain a lot of lycopene, and lycopene contains double bonds, right? Got that alkene, and lycopene is a known antioxidant. So it has these properties of, you know, being able to fight cancer, right? It's got these cancer fighting properties. And lycopene is more concentrated in those cooked tomatoes versus just the fresh tomatoes. But anyway, it's those double bonds are really important to that molecule, lycopene, as well. So we're going to find that alkenes are all over, that there's lots of double bonds, they're really reactive, and that they're really important to health in the human body. So what are some examples of molecules that can contain some of these alkenes or these double bonds? Well, here is an example of a fatty acid that has two double bonds, and even the type and geometry around the double bonds is going to be important, but let's just find those for now. We, from our functional groups, know that this functional group is a carboxylic acid, so we're going to be able to find lots of functional groups on these molecules as well. And if we take a look at this example of a lipid, in this example of a lipid, lipids have chains that are entirely saturated. So lots and lots of carbon-carbon single bonds. And then they can have some chains that have double bonds. So we can look for the chain in the lipid that has a double bond, and that chain itself would be unsaturated in that lipid. And then over here, we have all carbon-carbon single bonds, and so that would be saturated. This is what we call a triglyceride. We'll talk more about these, but try for the three different chains. So one is saturated, one is unsaturated, and then the next one is saturated. And then if we check this out, there is an, in the middle of the carbon chain, there's an O, C double bond O, and it's got carbon chains continuing in either direction. And there's actually three of those. There's 1, 2, 3 of these functional groups. So we know that functional group has an ester. So there's three esters in that lipid. Let's see. Well, we can look for the benzene functional group. That's when we have that hexagon with alternating double, single bonds. And there's quite a few of those here. Here's a benzene on the ibuprofen structure. Here's a benzene on the aspirin structure. Now in limonene, you might almost want to circle that, but it's not. That's got a hexagon with just one double bond. So that double bond is an alkene. But the ring, the hexagon with just one double bond, it's not a benzene. And then there's another double bond down here on limonene structure as well. So two alkenes, two alkenes on limonene. Over here in vitamin K3, we see a benzene ring. In phenylalanine, we see a benzene ring. Dopamine has a benzene ring. Let's come back to benzoate pyrene. Triclosan has two analogous benzene rings. It's almost a mirror image molecule, not quite, because we see an OH coming off of it, or an alcohol functional group. So we recognize a lot of functional groups from studying that. If we go back to dopamine, it had alcohols here as well. So here's an alcohol here and here on the ring. The NH2 was an amine functional group. Here's another amine functional group on phenylalanine. So there's an amine on it. Then we've got a C double bond O OH on there, and that's a carboxylic acid. So preview, that is going to be an amino acid. because it has both a carboxylic acid and an amine functional group on it. Going back to vitamin K3, here we see ketone functional groups because there's just a C double bond O in the ring, so there's a ketone. And not to miss the important alkene right here on the side of the molecule. So there's an alkene functional group. Going back to ibuprofen, here's a COOH. That's another way to realize that we have a carboxylic acid. So in phenylalanine, it was written as, a double line, a C double bond to O, and then the C had an OH. In ibuprofen, it just happens to be abbreviated again, COOH, abbreviated again in aspirin as well. So again, those COOHs were both carboxylic acids. And then we might want to see, well, what's going on with our benzoapyrene? It might be easy to spot benzene rings here and here, but these are actually all considered fused benzene rings. They share the double bonds, even, with molecules across from them. And each carbon has 4 bonds coming out of it. And it has 4 bonds, but each carbon is just connected to 3 other carbons. So that's kind of how we determine that these are actually considered like all fused benzene rings. And so it's a fused sheet of benzene rings. And eventually we can get, graphene sheets like that. So if benzoapyrene considered, continued with lots and lots of benzene rings, we would get graphite or, an elemental form of carbon. So eventually this likes to become graphene sheets, which is kind of fun. So I think that covers our functional groups. Oh, I noticed I missed one. I wonder if you're wondering and thinking of which functional group it is. In aspirin here, we've got one more functional group. There's a C double bond O, and then it's bonded to an O, and the carbons continue in both directions. So that one's an ester functional group. So hopefully I have selected all of the functional groups and left behind only alkane chains, only that single bonded chains. So in conclusion here, when we have saturated carbon chains, they are all single bonds. They are filled to capacity with hydrogen atoms. When we have unsaturation, we have either an alkene or an alkyne. We have maybe one or more single or double bonds. So saturated, all CC all CC single bonds is saturated. Unsaturated is when you have one or more carbon-carbon double bonds or carbon-carbon triple bonds. You won't be able to saturate or fill that to capacity with hydrogen atoms.